Hello everyone. Today we'll study transformation of functions. First of all, let me show you the graph of some special functions. f of x equal to x, f of s equal to s squared, f of s equal to s cubed. How do we graph these functions? We can sort of graph these functions by plotting points. So first of all, we make a table. For f of s equal to x, we first of all make a table. Make table for x and y. Usually we let y equal to this function f of x, which is x. Then we pick some value for x. Usually we pick some positive value and some negative value. Here we can pick -2, -1, 0, 1, and 2. Now, plotting these values into the function and find y. If I plot in -2, if I plug in -2 for x, I get -2 here because y equal to x. If I plug in -1 for x, I get -1 because y equal to x. If I plug in 0, I get 0. If I plug in 1, I get 1. If I plug in 2, I get 2. Then plot the points. Plot the points in the xy plane. First point, -2, -2. It's here. X is -2, y is -2. Second point, -1, -1. X is -1, y is -1. Next point, 0, 0 is here. Next point, 1, 1. X is 1, y is 1. Next point, 2, 2. X is 2, y is 2. Then connect all these points together, we have a line. So that's the graph of this function f of s equal to x. Next, let's sketch a graph of the function f of x equal to s squared. How do we graph this function? We make table. Make table for x and y. Let y equal to the function f of x equal to s squared. Then pick some value for x. In general, pick some positive value and some negative value for x. Here we can pick -2, -1, 0, 1, and 2. Pick some positive value and some negative value for x. And then plug in x, find y. If I plug in -2 here, I get -2 squared. -2 squared is 4. If I plug in -1 here, I get -1 squared. -1 squared is +1. If I plug in 0 here, I get 0 squared. 0 squared is 0. If I plug in 1, here I get 1 squared. 1 squared is 1. If I plug in 2, I get 2. I get 2 squared. 2 squared is 4. Then plot the points. First point, -2, 4. When s is -2, y is 4. When s is -2, y is 4. It's here. Second point, -1, 1. When s is -1, y is 1. It's here. Next point, 0, 0 is here. Next point, 1, 1 is here. Next point, 2, 4. S is 2, y is 4 is here. Then connect these points using smooth curves. Connect these points using smooth curves. That's the graph of the function f of x equal to s squared. So the graph of the function f of x equal to x looks like this. That's the graph of this function f of x equal to x. The graph of x squared looks like this. It's a U shape. Next, how do we graph the function f of x equal to x cubed? For the function f of x equal to x cubed, we can also make table. Make table for x and y. Let y equal to f of x, which is x cubed. Then pick some value for x and plug in x to find y. In general, we pick some positive value and negative value for x. We can pick -2, -1, 0, 1, and 2. Then plug in -2. If I plug -2 here, -2 cube, it means -2 times -2 times -2. -2 times -2 is positive 4. 4 times -1. 4 times -2. Double negative positive number times negative number is negative. That's -8. If we plug in -1, we get -1 cube. -1 cube is -1 times -1 times -1. -1 times -1 is positive 1. Positive 1 times -1 is -1. If we plug in 0, 0 cube means 0 times 0 times 0, which is 0. If I plug in 1, 1 cube means 1 times 1 times 1, which is 1. If we plug in 2, I get 2 cube. 2 cube means 2 times 2 times 2, which is 8, positive 8. Then we can plot these points and sketch a graph. Here x is 0, 1, 2, -1, -2. First point here is -2, comma -8. X is -2, y is -8. Let's make the scale in y-axis a little smaller. Say 1 is here, 2 is here, 3 is here, 4 is here, 5 is here, 6 is here, 7 is here, 8 is here. Make the scale in the y-axis a little smaller. So that's -1, -2, -3, -4, -5, -6, -7, -8. First point, x is -2, y is -8 is here. Second point, x is -1, y is -1, somewhere here. X is -1, y is -1. Next point, x is 0, y is 0. Next point, x is 1, y is 1. 1 is here. Next point, 2, comma 8. X is 2, y is 8. Then connect these points using smooth curves. Connect this point using smooth curve. That's the graph of the function f of x equal to x cubed. So the graph of this function f of x equal to x cubed looks like this. That's the graph of the function f of x equal to x cubed. And in general, for the function f of x equal to x raised to power n, if n is even, its graph looks like this. If n is even, all their graphs looks like this. They all look similar. They all have the same shape. For example, f of x equal to x to the power 4, f of x to the x to the power 6. As long as exponent is even, their graph all looks like this. They all have the same shape. And if n is odd, for the function f of x equal to x to the power n, if n is odd, their graph all looks like this. For the function f of x equal to x to the power 5, x to the power 7, as long as the power is odd, they all look like this. Their graph all looks similar as this. They all look similar for x to the power 5, x to the power 7, x raised to any odd power. Their graph all look similar to this. And these functions has a name. They are called power functions. These functions has a name. They are called power functions. X raised to the first power, second power, third power, and nth power in general. They are all called power functions. And the function f of x equal to x squared, this function has a special name. It's called the parabola. Only for the second degree function f of x equal to x squared, this function has a name called a parabola. Next, how do we graph the function f of x equal to absolute value of x? How to graph this function? So we can also make a table for this function. F of x equal to absolute value of x. Let's make a table for x and y. Let y equal to f of x, which is absolute value of x. Then pick some value for x. In general, you can pick some positive value and some negative value. Here we can pick -2, -1, 0, 1, 2. If I plug in -2 for x, I get absolute value of -2. Absolute value of -2 is +2. If I plug in -1 for x, I get absolute value of -1. Absolute value of -1 is +1. If I plug in 0, I get absolute value of 0, which is 0. If I plug in 1 for x, I get absolute value of 1. Absolute value of 1 is 1. If I plug in 2 for x, I get absolute value of 2. Absolute value of 2 is 2. So that's the table. Next, we can plot the points and sketch the graph. First point, -2, 2. X is -2, y is 2, it's here. Second point, -1, 1. X is -1, y is 1, it's here. Next point, 0, 0 is here. Next point, 1, 1 is here. Next point, 2, 2 is here. Then connect all these points. So that's the graph of the function f of x equal to absolute value of x. It's a V shape. It's a V shape. So the graph of f of x equal to absolute value of x looks like this. It has a V shape. This is called an absolute value function. This function has a name. It's called an absolute value function. Next, how do we graph the functions f of x equal to 1 over x and f of x equal to 1 over x squared? For these two functions, we can also graph them by plotting points. For the first function, f of x equal to 1 over x, let's first of all make a table for x and y. Y equal to f of x, which is 1 over x. Now, pick some value for x. Usually, pick some positive value and some negative value. Here, let's pick -2, -1, 0, 1, and 2. And then plug in. If I plug in -2 for x, I get 1 over -2. 1 over -2 is -1 over 2. If I plug in -1, I get 1 over -1. 1 over -1 is -1. If I plug in 0, it's undefined. If I plug in 0, it's undefined. So we cannot plug in 0. We need to plug in some number between 0 and -1. And some number between 0 and +1. We cannot plug in 0 directly. So here we need to plug in some number between 0 and -1. And some number between 0 and +1. We cannot plug in 0 directly. So for number between 0 and -1, let's pick some numbers. Let's pick a half and a third. -half, -a third. When we plug in 0, it's undefined. So we cannot plug in 0. We pick some number between 0 and -1. And then pick some number between 0 and +1. Pick some number between 0 and +1, I can pick a half and a third. Then plug in these numbers. If I plug in -half, what do we get here? If I plug in -half for x, what do I get? F of -half is 1 over -1 over 2. 1 divided by a fraction means we take 1 times its reciprocal. The reciprocal of -1 over 2 is -2 over 1, which is -2. So if I plug in -1 over 2, I get -2. What if I plug in -1 third? If I plug in -1 over 3, what do I get? Plug in -1 over 3 for x, I get 1 over -1 over 3. Number 1 divided by a fraction means we take number 1 times its reciprocal. The reciprocal of -1 third is -3 over 1, which is -3. So when I plug in -1 third, I get -3. When we plug in 0, it's undefined, so let's skip 0. If we plug in 1 third, I get 1 over 1 third. 1 divided by a fraction means 1 times its reciprocal. 1 times 3 over 1 is 3. So when I plug in 1 third, I get 3. When I plug in half, I get 1 over 1 over 2. 1 divided by a fraction means 1 times the reciprocal. 1 times 2 over 1 is 2. So when I plug in half, I get 2. When I plug in 1, I get 1 over 1, which is 1. When I plug in 2 for x, I get 1 over 2, which is 1 over 2. Then we can plot points and sketch a graph. When x is -2, y is -half. -half is somewhere between 0 and -1. It's here. That's the first point. When x is -2, y is -half. Second point, when x is -1, y is -1. It's here. Next point, when x is -half, y is -2. When x is -half, y is -2. Next point, when x is -1/3, y is -3. -1/3 somewhere here, y is -3. Then connect these points using smooth curves. Connect these points using smooth curve. That's one piece. Continue. When x is 1/3, y is 3. 1/3 somewhere here. Next, when x is half, y is 2. Next point, when x is 1, y is 1. When x is 2, y is half. Somewhere here. Then connect all these points using smooth curves. And here we can see that the curve eventually gets very, very close to the x-axis and the y-axis, but never touch the x-axis and the y-axis. These two lines, they are called asymptotes. This line is called the vertical asymptote. And this line is called the horizontal asymptote. These two lines are called asymptotes because the curve gets very, very close to the line but never touch the line. So they are called asymptotes. This line is called a vertical asymptote. This line is called a horizontal asymptote. So that's the graph of the function f of x equal to 1 over x. It looks like this. The curve gets very, very close to the x and y axis, but never touch the axis. The curve gets very, very close to the axis, but never touch the never touch the axis. That's the graph of the function f of x equal to 1 over x. Next, let's graph this function f of x equal to 1 over x squared. For this function f of x equal to 1 over x squared, we can also sketch a graph by plotting points. So make table for x and y. Y equal to f of x, which is 1 over x squared. Usually you pick some positive value for x and some negative value for x. -2, -1. Since x cannot be 0, so pick some number between -1 and 0, say -half and -1/3. On the other side, pick some number between 0 and +1. I can pick +half and +1/3. And then I can pick number 2 for x. When plotting 0 for x, it's undefined. 1 over 0 squared is undefined. Denominator cannot be 0. It's undefined. Then plug in each x value and find y. If I plug in -2, f of -2 is 1 over -2 squared, plug in -2 for x, which is 1 over 4. If we plug in -1, we get 1 over -1 squared. -1 squared is +1, so we get 1 over 1. 1 over 1 is 1. So if I plug in -1, I get +1. If I plug in -1 over 2, I get 1 over -1 over 2 squared. -1 over 2 squared is 1 over 4. 1 divided by 1 over 4 means 1 times its reciprocal. 1 times 4 over 1, which is +4. So if I plug in -1 over 2, I get +4. If I plug in -1/3, -1/3 squared. -1/3 squared is 1 over 9. 1 divided by 1 over 9 is 1 times its reciprocal. 1 times its reciprocal. 1 times 9 over 1 is 9. So if I plug in -1/3, I get +9. If I plug in 1/3, I get 1 over 1/3 squared. 1/3 squared is 1 over 9. 1 divided by 1 over 9 means 1 times its reciprocal. 1 times 9 over 1 is 9. If I plug in half, I get f of half. If I plug in half here, I get 1 over half squared. Half squared is a quarter. 1 over a quarter means 1 times its reciprocal. 1 times 4 over 1 is 4. So if I plug in half, I get 4. If I plug in 1, I get 1 over 1 squared. 1 squared is 1. 1 over 1 is 1. If I plug in 2 for x, I get f of 2, which is 1 over 2 squared. 2 squared is 4. So the answer is 1 over 4. When I plug in 2, I get 1 over 4. Next, practice points and sketch a graph. Zero, 1, 2, -1, -2. When s is -2, y is 1 over 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. When s is -2, y is 1 over 4. 1 over 4, somewhere very, very close to 0, is here. When s is -1, y is +1. When s is -half, y is 4. -half somewhere here, y is 4. When s is -1/3, y is 9. -1/3 somewhere here is very close to 0. Y is 9. Then connect these points using smooth curves. Continue. When x is 1/3, y is 9. 1/3 is here, y is 9. When x is 1/3, y is 9. When x is half, y is 4. Half is here, y is 4. When x is 1, y is 1. When x is 2, y is 1/4. Somewhere here. Then connect points using smooth curves. Connect these points using smooth curves. Make the curve smooth. Again, in this graph, the curve gets very, very close to the x-axis and the y-axis, but never touching the axis. The curve gets very, very close to the x-axis and the y-axis, never touching the x-axis. So they are called asymptotes. This is the vertical asymptote. And this is a horizontal asymptote. That's the graph. F of x equal 1/s squared. That's the graph. F of x equal to 1/s squared. That's the horizontal asymptote, and that's the vertical asymptote. The curve never touches the asymptote. The curve never touches the asymptote. In general, for the function f of x equal to 1/x to the power n. In general, for the function f of x equal to 1/x to the power n, if n is odd, their graph all have this shape. If n is odd, their graph all have this shape. For the function f of x equal to 1/x cubed, f of x equal to 1/x to the power 5, they all have this shape. And if n is even, their graph all have this shape. They all have this shape. When n is even, for example, f of x equal to x raised to power 4, f of x equal to x raised to 1/x to the power 4, f of x equal to 1/x raised to power 6, they all have this shape. When n is even, their graph all looks like this. And for all these graphs, they are horizontal asymptote their horizontal asymptote is this line, the x-axis. The x-axis goes through 0 on the y-axis, so that's the line y equal to 0. That's the horizontal asymptote for all its graph. So for all its graph, their horizontal asymptote is this line, y equal to 0. Their vertical asymptote is this line, the y-axis. And this vertical line goes through 0 in the x-axis. So the vertical asymptote is always a line, x equal to 0. So for all its graph, their horizontal asymptote is the line y equal to 0. That's their horizontal asymptote. Their vertical asymptote is the line x equal to 0. That's their vertical asymptote. All these functions has a name. They are called the reciprocal functions. They are called the reciprocal functions. They are called reciprocal functions. All these functions has a name. They are called reciprocal functions. And this function, f of x equal to 1 over x, this function has a special name. It's called a hyperbola. This graph is called a hyperbola. Only for this graph, it has a name called hyperbola. This function is called this graph is called hyperbola. That's the graph of reciprocal functions. Next, how do we graph the function f of x equal to square root of x and f of x equal to cube root of x? For these two functions, we can also try to plot points. The first function, f of x equal to square root of x. Let's make a table for x and y. Let y equal to f of x, which is square root of x. In general, we pick some positive value and some negative value for x. Here, let's try -2, -1, 0, 1, and 2. If we plug in -2, what we get? If we plug in -2, what do we get here? If we plug in -2 for x, what do we get? We get square root of -2. We know that square root of negative number is undefined. Square root of negative number is undefined, so we cannot plug in negative numbers. The number under the square root must be greater than or equal to 0. So we cannot plug in negative numbers. For this function, we cannot plug in negative numbers. So let's plug in some positive number. Let's try 0, 1, 2, 3, 4. Let's plug in some positive numbers. If I plug in 0, what do we get? Square root of 0 is 0. If we plug in 1, square root of 1 is 1. If I plug in 2, square root of 2 is not a nice number. So here I use calculator. I get 1.414. I use calculator. I get 1.414. If I plug in 3, I get square root of 3. Again, I use calculator here. Square root of 3 is 1.732. Next, plug in 4, I get square root of 4. Since 2 times 2 is 4, square root of 4 is 2. Next, let's plot points. When x is 0, y is 0. The point here is 0, 0. When x is 1, y is 1. The point is 1, 1. when x is 2, y is 1.414. When x is 2, y is 1.414. Somewhere here. When x is 3, y is 1.732. Somewhere here. When x is 4, y is 2. Then connect these points using smooth curve. On the right side, the curve continues, but on the left side, the curve terminates here. S cannot be negative. On the left side, the curve terminates here. On the right side, the curve continues, but on the left side, the curve terminates here, because S cannot be negative. The number under the square root cannot be negative. So that's the graph of the function f of x equal to radical x. So for this function f of x equal to radical x, it looks like this. The graph looks like this. That's the graph of this function. Next, f of x equal to cube root of x. How do we graph this function? F of x equal to cube root of x. We can also graph this function by plotting points. Let's make a table for x and y. Y is always f of x, which is cube root of x. We know for square root of x, we cannot plot in negative numbers for square root. But for cube root, we can plot in both positive and negative numbers. So let's pick some value for x. Some positive number, some negative number. Here we can pick negative 2, negative 1, 0, 1, and 2. If we plug in negative 2, for x, we have cube root of negative 2. Cube root of negative 2. Here I use my calculator. I get negative 1.260. If I plug in negative 1, I get cube root of negative 1, which is negative 1. If I plug in 0, I get cube root of 0. Cube root of 0 is 0. If I plug in 1 for x, I get cube root of 1. Cube root of 1 is 1. If I plug in 2 for x, I get cube root of 2. Cube root of 2, if I use my calculator, I get 1.260. Then plot these points. Then plot these points and sketch the graph. First point, negative 2 comma negative 1.260. X is negative 2, y is negative 1.260. Somewhere here. That's the first point. X is negative 2, y is negative 1.260. Next, x is negative 1, y is negative 1. It's here. Next point, 0, 0 is here. Next point, 1, comma 1 is here. Next point, s is 2, y is 1.260. S is 2, y is 1.260, somewhere here. Then connect these points using smooth curves. Connect these points using smooth curve. That's the graph of this function. F of x equal to cube root of x. So the graph of this function looks like this. That's the graph of this function, f of x equal to cube root of x. And in general, for the function f of x equal to n root of x, in general, for the function f of x equal to n root of x, if n is even, the graph looks like this, have very similar shape as this graph. If n is even. The graph looks very similar as this graph. In general, when n is 4, when f of x equal to the 4th root of x, equal to the 6th root of x, and so on, their graph all have this shape. And for the function f of x equal to n root of x, if n is odd, their graph all looks like this. That means for the functions f of x equal to the 5th root of x, f of x equal to the 7th root of x, their graph all looks like this. Their graph all similar to this. And functions of this type, they are called root functions. Functions of this type are called root functions. So those are the graphs of some special functions. Power functions, absolute value functions, reciprocal functions, and root functions. Memorize all these special functions. Memorize the graph of these special functions. Next, I'll show you how to graph more complicated graph based on these special functions. The first type of transformation of functions is called horizontal shifting. Before I explain to you what's horizontal shifting, let me show you an example first. Graph the functions f of x equal to square root of x, g of x equal to square root of x plus 1, and h of x equal to square root of x minus 2 in the same coordinate plane. So, in order to graph these three functions in the same coordinate plane, let's first of all make a table for each of them first. Let's make a table for each of them. First function, f of x equal to square root of x. Second function, g of x equal to square root of x plus 1. The third function, h of x equal to square root of x minus 2. So let's make a table for each of them. For the first function, f of x equal to square root of x. Make a table for x and y. Y equal to f of x, which is square root of x. We know that for square root of x, what's under square root must be greater than or equal to 0. So we cannot pick negative numbers. The value we pick must start from 0. So we can pick 0, 1, 2, 3, and 4. For the second function, for function g, what's under square root cannot be negative. So x plus 1 must be greater than or equal to 0. if I isolate x must be greater than or equal to -1. So for the second table, we start from -1. Y here equal to g of x, which is square root of s plus 1. For the second function here, x start from -1. So I can pick -1, 0, 1, 2, 3. For the third function, we know what's under square root cannot be negative. So s minus 2 must be greater than or equal to 0. If I add 2 to both sides, s must be greater than or equal to 2. So the value we pick must start from 2. It cannot be less than 2. Y must be h of x, which is square root of s minus 2. Then pick some value for x. S must be greater than or equal to 2. So I can pick 2, 3, 4, 5, and 6. Now plug in numbers. If I plug in 0 for x, square root of 0 is 1. If I plug in 1 for x, square root of 1 is 1. Square root of 0 is 0. If I plug in 0, square root of 0 is 0. If I plug in 1, square root of 1 is 1. If I plug in 2, square root of 2. Square root of 2, I use my calculator, is 1.414. If I plug in 3, square root of 3 is 1.732. I use my calculator here. If I plug in 4, square root of 4 is 2. That's the first table. Second table, if I plug in -1, if I plug in -1 for x, -1 plus 1 is 0. Square root of 0 is 0. If I plug in 0 for x, 0 plus 1 is 1. Square root of 1 is 1. If I plug in 1 for x, 1 plus 1 is 2. Square root of 2, I use my calculator, is 1.414. If I plug in 2, 2 plus 1 is 3. Square root of 3 is 1.732. If I plug in 3 for x, 3 plus 1 is 4. Square root of 4 is 2. Next table. If I plug in 2 for x, 2 minus 2 is 0. Square root of 0 is 0. If I plug in 3, 3 minus 2 is 1. Square root of 1 is 1. If I plug in 4 for x, 4 minus 2 is 2. Square root of 2 is 1.414. If I plug in 5 for x, 5 minus 2 is 3. Square root of 3 is 1.732. If I plug in 6 for x, 6 minus 2 is 4. Square root of 4 is 2. So here we make a table for each function. Next, let's graph these functions in the same coordinate plane. Let's graph function f first. For function f, first point is 0, 0. S is 0, y is 0. Second point, 1, 1. S is 1, y is 1. Next point, 2, 1.414. 2 is here, 1.414 somewhere here. Next point, 3, 1.732. 1.732 somewhere here. Next point, 4, 2. S is 4, y is 2, somewhere here. Then connect these points using smooth curves. Let's use a smooth curve, connect these points. That's the graph of the function y equal to f of x, which is square root of x. Next, let's graph function g. For function g, first point is -1, 0. S is -1, y is 0, is here. Next point, 0, 1. X is 0, y is 1. It's here. Next point, 1, 1.414. X is 1, y is 1.414. Next point, 2, 1.732. X is 2, y is 1.732. Somewhere here. Next point, 3, 2. X is 3, y is 2. Somewhere here. Then connect all these points using smooth curve. That's a graph of g. Y equal to g of x, which is square root of x plus 1. Next, let's graph function h. For function h, first point is 2, 0. X is 2, y is 0. It's here. Next point, 3, 1. X is 3, y is 1. Next point, 4, 1.414. X is 4, y is 1.414. Somewhere here. Next point, 5, 1.732. X is 5, y is 1.732. Somewhere here. Next point, x is 6, y is 2. X is 6, y is 2. Then connect these points using smooth curve. Next graph, y equal to h of x, which is square root of x plus 1. Square root of x minus 2. Function f is square root of x. Now, let's observe these three graphs. Observe these three graphs. It looks like function g is 1 unit to the left of function f. It looks like function g is 1 unit to the left of function f. And function h is 2 units to the right of function f. It looks like function h is 2 units to the right of function f. It looks like function g is 1 unit to the left of function f. And function h is 2 units to the right of function f. Or in other words, if I shift function f 1 unit to the left, I get function g. If I shift function f 2 units to the right, I get function h. So based on this example, let me introduce horizontal shifting. Suppose the graph of y equal to f of x is known. Let c be a positive number. To graph y equal to f of x plus c. To graph the function y equal to f of x plus c. Shift the graph y equal to f of x c units to the left. To graph the function y equal to f of x minus c. Shift the graph y equal to f of x, c units to the right. Which means if I add c to x, I shift the graph c unit to the left. If I subtract c from x, I shift the graph c unit to the right. So here, compare function, in this example, compare function f and g. If I add 1 to x, I shift function f 1 unit to the left. Look at function h. If I subtract 2 from x, I shift function f 2 units to the right. So if I subtract, shift to the left. If I add, shift to the right. That's called horizontal shifting. Another transformation of functions is called vertical shifting. Before I explain to you what's vertical shifting, let's look at an example first. Graph the functions. F of x equal to square root of x. G of x equal to square root of x plus 3. This 3 is outside square root. And h of x equal to square root of x minus 4. This 4 is outside square root in the same coordinate plane. So again, let's make a table. In this example, f of x is square root of x. G of x is square root of x plus 3. H of x is square root of x minus 4. For each function, the domain is s greater or equal to 0, s greater or equal to 0, x greater or equal to 0. Make table for each function. Make table for x and y for each function. So for the first function, pick some value for x. Since x must be greater or equal to 0, I can pick 0, 1, 2, 3, 4. If I plug in 0, I get 1. Plug in 1. So if I plug in 0, I get 0. If I plug in 1, I get 1. If I plug in 2, square root of 2 is 1.414. If I plug in 3, I get 1.732. If I plug in 4, square root of 4 is 2. For function g, make table for x. Make table for x and y. Y equal to g of x, which is square root of x plus 3. Pick some value for x. Here, x must be greater or equal to 0. So I can pick 0, 1, 2, 3, 4. If I plug in 0 for x, square root of 0 is 0. 0 plus 3 is 3. If I plug in 1 for x, square root of 1 is 1. 1 plus 3 is 4. If I plug in 2 for x, square root of 2 is 1.414. 1.414 plus 3 is 4.414. If I plug in 3 for x, square root of x is square root of 3 is 1.732. 1.732 plus 3 is 4.732. If I plug in 4 for x, square root of 4 is 2. 2 plus 3 is 5. Next, let's make table for function h. y is h of x, which is square root of x minus 4. Here, domain of x is x greater or equal to 0. So pick some number greater or equal to 0. I can pick 0, 1, 2, 3, and 4. If I plug in 0 for x, square root of 0 is 0. 0 minus 4 is negative 4. If I plug in 1, square root of 1 is 1. 1 minus 4 is negative 3. If I plug in 2, square root of 2 is 1.414. 1.414 minus 4 is negative 2.586. If I plug in 3, square root of 3 is 1.732. 1.732 minus 4 is negative 2.268. If I plug in 4 for x, square root of 4 is 2. 2 minus 4 is negative 2. Then let's sketch a graph based on this table. Let's graph the functions in the same coordinate plane based on this table here. Let's graph function f first. In function f, first point is 0, 0, which is here. Second point 1, 1. Next point 2, 1.414. 2 is here, 1.414 somewhere here. Next point 3, 1.732 somewhere here. Next point 4, 2 somewhere here. Then connect all these points using smooth curve. Next, let's graph function g. This is function f. Next, let's graph function g. In function g, first point is 0, 3. X is 0, y is 3. Somewhere here. X is 0, y is 3. Second point 1, 4. X is 1, y is 4. Somewhere here. Next point 2, 4.414. X is 2, y is 4.414. Somewhere here. Next point 3, 4.732. X is 3, y is 4.732. Somewhere here. Next point x is 4, y is 5. 4, 5. Somewhere here. Then connect all these points using smooth curve. Use a smooth curve. Connect all these points. That's the function g of x, which is square root of x plus 3. Next, graph function h. First point 0, -4. X is 0, y is -4. Somewhere here. Next point 1, -3. X is 1, y is -3. X is 1, y is -3 somewhere here. Next point 2, -2.586. X is 2, y is -2.586 somewhere here. Next point 3, -2.268. S is 2, y is negative 2.268. S is 3, y is negative 2.268. Next point, 4 comma negative 2. S is 4, y is negative 2. Somewhere here. Then connect all these points using a smooth curve. That's the graph y equal to h of x, which is square root of x minus 4. If we observe this graph, you can see that function g, it looks like function g is 3 units above function f. Function g is about 3 units above function f. And function h is about 4 units below function f. Function h looks like it's 4 units below function h. Sorry, function h is 4 units below function f. 0, 1, 2, 3, 4. It's about 4 units below function h. And function g is about 3 units above function f. So based on this graph, let me introduce vertical shifting. Suppose the graph y equal to f of x is known. Let C be a positive number. To graph the function y equal to f of x plus c. This c is outside parentheses. To graph the function y equal to f of x plus c, shift the graph of y equal to f of x c units upward. To graph the function y equal to f of x plus c, shift the graph of y equal to f of x c units upward. To graph the function y equal to f of x minus c, this c is outside parentheses. This plus minus c, they are both outside parentheses. Shift the graph of y equal to f of x c units downward. So that means if I add c to the function, f, I shift the graph c units upward. If I subtract c from the function, I shift the graph c units downward. So here, suppose the graph of f is known. If I add 3 to the entire function, I shift function f 3 units upward, I get function g. For function h here, if I subtract 4 to the entire function, I shift the graph f 4 units downward. If I subtract 4 from function f, I shift the graph 4 units downward. So for horizontal shifting, the number c is inside parentheses, is next to x. We add or subtract c from x. For horizontal shifting, we add or subtract x. We add or subtract c from x. C is inside parentheses. For vertical shifting, c is outside parentheses. We add or subtract c to the entire function. C is outside parentheses. For vertical shifting, c is outside parentheses. For horizontal shifting, c is inside parentheses. We add or subtract from x. We add to x or subtract from x. C is inside parentheses. For horizontal shifting, c is inside parentheses. For vertical shifting, we add or subtract to the entire function. C is outside the parentheses. Now, Before I show you more transformations of functions, let me show you some examples first. Graph each of the following functions. Using transformation of functions. First example, graph of the function f of x equal to x plus 2 cubed. How do we graph this function using transformation? First of all, observe the function. Compare the function with those special functions here. This function looks like the function s cubed here. This function s plus 2 cubed, it looks like this function here. So we can use this function as a parent function. So first of all, pick parent function. We use this function as a reference. Let's call it parent function. Y equal to s cubed. This function looks like a special function f of x equal to s cubed. So we use this function as a parent function. Start from this function. Try to do some transformation to get this function here. The graph of y equal to s cubed looks like this. That's the graph y equal to s cubed. Now, if I add 2 to x, what should we do here? According to horizontal shifting, if I add c to x, I shift the graph c unit to the left. If I add c to x, I shift the graph c unit to the left. So here, if I add 2 to x, I shift this graph 2 unit to the left. When I add 2 to x, I shift the graph 2 units to the left. So when I add 2 to x, I shift this graph 2 units to the left. This point, it was 0. If I shift it 2 units to the left, it becomes -2. This point, it was 0. If I shift it 2 units to the left, it becomes -2. So I shift this graph 2 units to the left. I get this graph. That's the graph of this function f. That's the graph of this function f. Y equal to x plus 2 to the power 3. That's the graph of this function f. Next example. F of x equal to absolute value of x plus 3. F of x equal to absolute value of x plus 3. So first of all, find a parent function from these special functions. From these special functions, find a parent function. It looks like this function here. Absolute value of x plus 3. It looks like this function here. So here I'll use y equal to absolute value of x as parent function. First step, choose a parent function. Here I'll choose y equal to absolute value of x. I choose this function as a parent function. And we need to memorize the graph of the parent function. The graph of the parent function looks like this. It's a V shape. For absolute value of x, the graph is a V shape. Now, when I add 3 to the function, this 3 is not next to x, it's outside. This 3 is not next to x, it's outside the absolute value. If I add 3 to the entire function, what do we get? Here. If I add 3 to the entire function f, to the entire function, I shift the graph c units upward. If I add c to the entire function, I shift the graph c units upward. So if I add 3 to the entire function, I shift this graph 3 units upward. Shift this graph 3 units upward. This point, it was 0 here. If I shift it 3 units upward, it's called 1, 2, 3. Let's call it 3 here. If I shift this graph 3 units upward, it looks like this. That's a graph y equal to absolute value of x plus 3. Next example. F of x equal to 1 over x minus 1. So first step, find a parent function first. How this function looks like. Observe these special functions. Observe these special functions. It looks like the hyperbola. F of x equal to 1 over x. Looks like this function. So I choose y equal to 1 over x as a parent function. The graph of a parent function looks like this. We need to memorize the graph of a parent functions. This is the vertical asymptote. This is vertical asymptote. And this line is horizontal asymptote. That's the parent function. Now, let's graph 1 over y equal to 1 over x minus 1. If I subtract 1 from x, how does the graph look like? If I subtract 1 from x, what should we do here? If we subtract 1 from x, in general, if we subtract c from x, we shift the graph c units to the right. If we subtract c from x, I shift the graph c units to the right. So that means if I subtract 1 from x, I shift this graph 1 unit to the right. So shift the graph. One unit to the right. Shift this graph 1 unit to the right. Now, if a graph has asymptotes when we shift, the asymptote will be shifted at the same time. If a graph has asymptotes, when we shift the graph, asymptote will be shifted at the same time. So, if I shift the graph horizontally to the right, it was 0 here. If I shift this graph 1 unit to the right, the vertical asymptote goes to 1. If I shift this graph 1 unit to the right, the vertical asymptote will be shifted at the same time. It becomes 1 here. That's the new vertical asymptote. If I shift the graph to the right, horizontal asymptote stays the same. Horizontal asymptote stays the same. So that's the graph. That's the new vertical asymptote. Here, the new vertical asymptote here is x equal to 1. This line is x equal to 1. That's the new vertical asymptote. It was 0 here. When I shift it 1 unit to the right, become x equal to 1. That's the new vertical asymptote. Horizontal asymptote stays the same. It's y equal to 0. It stays the same. Next example. F of x equal to 1 over x plus 2. F of x equal to 1 over x plus 2. So this function also looks like this. We can choose the same parent function here. We can choose the same parent function, y equal to 1 over x. This function also looks like this. We can choose the same parent function. That's the vertical asymptote. That's the horizontal asymptote. We need to memorize all those special functions and use them as parent functions. Now, if I add 2 to the entire function, here we don't add 2 to x, we add 2 to the entire function. If we add 2 to the entire function, if we add c to the entire function, we shift the graph c units upward, which means if I add 2 to the entire function, I shift the entire graph 2 units upward. So shift the graph 2 units upward. When we shift the graph, the asymptote will be shifted at the same time. When we shift the graph upward, it was 0 here. Horizontal asymptote will be shifted upward at the same time. When we shift the graph upward, the horizontal asymptote will be shifted at the same time. And vertical asymptote here stays the same. Let me call this 1, call this 2 here. Horizontal asymptote, it was 0. When I shift it upward, asymptote will be shifted at the same time. When I shift the graph upward, asymptotes will be shifted at the same time. So horizontal asymptote become 2. That's the new horizontal asymptote. Vertical asymptote stays the same. So that's the horizontal asymptote. That's the vertical asymptote. Here, vertical asymptote stays the same. It's s equal to 0. Horizontal asymptote, we shift it 2 units upward. That's y equal to 2. It goes through 2 in the y-axis. So that's y equal to 2. That's the graph of this function. Next. F of x equal to square root of x plus 1 minus 3. F of x equal to square root of x plus 1 minus 3. First step, choose a parent function. When we're choosing parent function, in general, we can try to drop all numbers. If we drop all the numbers, what's left is square root of x. If we drop all the numbers, what's left is square root of x. So we can use square root of x as a parent function. In general, when we choose parent function, I can drop all the numbers. So I can choose square root of x as parent function. In general, when we choose parent function, I can drop all numbers. If I drop number 1, I get 1 over x. If I drop number 2, I get 1 over x. If I drop number 2, I get x cubed. If I drop number 3, I get absolute value of x. In general, when we choose parent functions, we drop all the numbers. We drop all the numbers. That's the parent function. The graph of square root of x looks like this. We need to memorize all parent functions. The graph of square root of x looks like this. First of all, let's graph the parent function. That's the parent function. Now we have square root of x plus 1 minus 3. This 1 is next to x. This 3 is outside the square root. So in order to graph this function, it takes 2 steps. Let's take care of what's inside first. When we add 1 to x, what should we do? When we add 1 to x, when we add c to x, we shift the graph c units to the left. So when I add 1 to x, I shift the graph 1 unit to the left. So first step, I try to graph, take care of the inside first. I shift the graph 1 unit to the left. I shift this graph 1 unit to the left first. This point it was 0. If I shift it 1 unit to the left, it becomes -1. This point it was 0. If I shift it 1 unit to the left, it becomes -1. Next, let's take care of -3 here. When I subtract 3 from the function, what should we do? When we subtract c from the function, we shift the graph c units downward. When we subtract c from the function. So when I subtract 3 from the function, I shift this graph 3 units downward. So shift this graph 3 units downward. Shift this graph 3 units downward. So that's the graph y equal to square root of x plus 1 minus 3. When I subtract 3 from the function, I shift it 3 units downward. This point, if I shift it 3 units downward, 1, 2, 3 is here. If I shift this point 3 units downward, it's here. Then the graph looks like this. And this point here is -1, -3. If I shift this point 3 units downward, it's -1, -3. And that's the graph of this function. Next, graph of the function f of x equal to 1 over x minus 1 minus 2. F of x equal to 1 over x minus 1 minus 2. So let's find the pattern function first. Find the pattern function first. In general, when we try to find a pattern function, we can drop all the numbers. If we drop all the numbers, what we have is y equal to 1 over x. If we drop all the numbers, what we have is 1 over x. So we can use 1 over x as a pattern function. We need to memorize the graph of a pattern function. It looks like this. That's the pattern function. This is the vertical asymptote. This line is vertical asymptote. This line is horizontal asymptote. If a graph has asymptote, we need to label the asymptote. That's the vertical asymptote. That's the horizontal asymptote. Now, here we have x minus 1 and then minus 2. That means it takes 2 steps. Let's take care of what's in the fraction first. If I subtract 1 from x, what should we do? In general, if we subtract c from x, we shift the graph c units to the right. If we subtract c from x, we shift the graph c units to the right. If I subtract 1 from x, I shift this graph 1 unit to the right. So, if we try to graph 1 over s minus 1, we shift this graph 1 unit to the right. Shift this graph 1 unit to the right. If I shift this graph 1 unit to the right, vertical asymptote, it was 0 here. If I shift it 1 unit to the right, it becomes 1. It was 0 here. If I shift it 1 unit to the right, it becomes 1. That's the new vertical asymptote, which is x equal to 1. Horizontal asymptote stays the same. It was y equal to 0. It stays the same. Then that's the new graph. Next, we subtract 2 from the entire function. If we subtract 2 from the entire function, we shift the graph 2 units downward. If we subtract 2 from the entire function, shift the graph 2 units downward. Next, for the graph y equal to 1 over s minus 1 minus 2, shift the graph 2 units downward. Shift the graph 2 units downward. Shift this graph 2 units downward. When I shift the graph downward, vertical asymptote stays here at 1. Vertical asymptote stays here. When I shift the graph downward, vertical asymptote stays here. For horizontal asymptote, if I shift the graph downward, it will be shifted down at the same time. For horizontal asymptote, if I shift it downward, it will be shifted at the same time. So I shift it 2 units downward. 1, 2, it's negative 2. It was 0. If I shift it 2 units downward, it was y equal to 0. If I shift it 2 units downward, it becomes y equal to negative 2. So that's the horizontal asymptote. It's y equal to -2. Vertical asymptote stays the same. It's x equal to 1. Then sketch the graph. The same graph, we'll put it here. The graph never touches the asymptote. That's a graph to this function.